Good day, I'm Norman Wahlberger. Today we're going to look at the extended rational numbers and how they can come up in practice. We'll have a look at how they can help us in analysis, how they can help us in projective geometry, and how they can shed some light on the geometry of a circle. And we'll start out by reviewing these somewhat new algebraic objects, an extension of the rational number system to include infinity. Okay, so here are the rational numbers, and here is this new number system that we've recently introduced, the extended rational numbers. This is not the only possible way of extending the rational numbers. There are lots of different ways of enlarging our number system. For example, later on we're going to talk about complex rational numbers, where we extend the rational numbers by adjoining a so-called square root of -1, or I. We'll also go in a different direction, adjoining a so-called square root of 2, purely algebraically. We've already talked about the rational polynumbers, which are another way of extending, a big way of extending the rational numbers to a larger arena. And there's lots of ways of combining things. So, for example, we could include an algebraic square root of 2 and an algebraic square root of 3 at the same time. Many, many more possibilities, all centered on the rational number system, which sits right at the heart of mathematics. And the real numbers, in case I haven't told you before, play no role. The real numbers are a fiction. They are a fantasy, a modern fantasy, which we are determined to shoot down. Okay, and we're going to do that. In fact, this part of this series is really geared towards that, to cutting down the various erroneous views of the real numbers that are currently out there. Okay, so one of the nice things about doing what we're doing here is that it gives you an example of an approach to extending the number system. I want to make sure that we are adopting a good point of view towards logical rigor, that we're going to be clear about the objects or expressions that form the basis of our arithmetic. When we're defining an extension of a number system or a new number system, we have to make sure that we're very, very clear about what the objects are. Or the way I like to think about it, the expressions that we write down on the paper. We've got to be precise about the operations and the laws they satisfy. There can be no possible ambiguity. We must be careful about proofs. Proofs are an essential aspect of such things. And throughout, we are guided by examples and computations. We want to look at a lot of examples and make a lot of computations so that we become confident about the validity of the various abstract things that we've written down. Without anchoring a theory in examples and computations, it's very easy to let it be like a hot air balloon. It just ends up in the stratosphere beyond logical grasp. Okay, we want to avoid that. We want to avoid the current unfortunate affairs that are centered around the real numbers. So although we introduced the extended rational numbers by first starting with integral points in the plane and defining appropriate operations on them, in retrospect, it's possible to start just from the extended rational numbers and to define them as follows. So an extended rational number is a pair, an ordered pair, A, B of integers, written more usually as A over B. And crucially, there's no restriction on the integers A and B. So B does not have to be non-zero. B is allowed to be 0. With this notion of equality, that A over B equals C over D, precisely when this condition is satisfied, Now this is not the first definition that I gave in my last talk. I had another definition which was a little bit wordier and which turned out not to be such a good one. A perceptive viewer noticed that that definition that I wrote down had a slight problem. The problem was that, according to that definition, 0 over 0 is not equal to 0 over 0. Okay? We do want 0 over 0 to equal 0 over 0. So I'm going to shift to this definition of equality for these pairs. Okay, what is it? Let's have a look. So A over B equals C over D precisely when there exist non-zero integers m and n satisfying, all right, either of these two conditions. They're really the same. So here is the condition in terms of integral points, that m times the point AB equals n times the point CD. And what that means is exactly this. It means that m times A equals n times C, and m times B equals n times D. So you can think that a certain multiple of the first pair is equal to a certain multiple of the second pair. And both of those multiples have to be non-zero. If that's satisfied, then A over B is said to be equal to C over D. Now, if neither of A, B, or C, D is equal to 0, 0, then you can try to check that this is equivalent to the simpler, more familiar condition that AD minus BC equals 0. Okay, here's a good exercise to show that this notion of equality enjoys a transitive property. Namely that if A over B equals C over D, and if C over D equals E over F, in this sense, then A over B equals E over F. So if there's a pair MN for this equality, and there's another pair, say LK or whatever, for this equality, then you can find a pair for this equality. Any notion of equality ought to have such a transitive aspect, otherwise it sort of doesn't sync with our natural intuition about what equality means. So this is a good thing to check for any notion of equality. So that's what an extended rational number is. It's an ordered pair of integers together with this notion of equality. So we have our numbers. Now we have to define operations. There are 4 operations: addition, multiplication, subtraction, and division. And here are the operations on them. So A over B plus C over D is this. A over B times C over D is this. A over B minus C over D is this. And A over B divided by C over D is this. Okay, and then these operations are well defined, meaning that if you replace A over B with an equal fraction, say E over F, then what you're going to get on this side is equal to what you get with the A over B. So the operations are well defined. And they are valid for any values A, B, C, D, integer values. There's no restriction on denominators. And it turns out they obey the usual commutative, associative, distributive laws. For example, P plus Q equals Q plus P. P plus Q minus R is P plus Q minus R. Distributive law, P times Q plus R equals P times Q plus P times R, and so on. And this new number system, which we are going to call the extended rationals, or RAT infinity, has some special elements that play an important role. So 0 over 1 is an important thing, usually called 0. 1 over 1, usually called 1. Minus 1 over 1, usually called minus 1. These are familiar rational numbers. But we also have some unfamiliar new numbers, 1 over 0, which we're writing also with this symbol and calling it infinity, and 0 over 0, which we're writing with this symbol, and we don't quite yet have a name for that. We're all thinking about what a good name for 0 over 0 is. Alright, so the operations are completely cut and dried. One can check all the laws. Please do. Please work out lots of examples. Convince yourself that this arithmetic really is consistent, that there are no logical errors anywhere. And if there are, please don't be afraid of embarrassing me. Send a comment. Say, this law doesn't work, or this relation doesn't hold. You've got to make sure that everything works. And examples and computations are the way, practically speaking, that we check that. And now it's interesting to observe that the familiar rational numbers that we learnt about back in primary school can actually be recovered from these extended rational numbers. And how do we do that? How do we get rational numbers from rational numbers with infinity? Well, first of all, we have to restrict our attention to those extended rational numbers a over b, where b is not equal to 0. That's the familiar look of a rational number. And then we can replace the equality with the simpler equality, because now these guys are never both 0. So the notion of equality becomes simpler. Just a over b equals c over d, precisely when AD minus BC equals 0. The 4 operations are just as before, but there is one important thing that we're prohibited from doing, that we used to be able to do up here, but we are no longer able to do in this domain. What's that? We are not allowed to divide by 0. So we are not allowed to take a over b divided by 0 over 1. We exclude that, because if we did that, then the result would be a rational number with a 0 in the denominator, which we're agreeing is out of the picture. So arguably, the case could be made that the extended rational number system is actually more natural than the rational number system. There are no sort of strange prohibitions. The extended rational number systems works with all pairs a over b, and all of the operations are well defined, even division, all the time. Okay, but a natural question is, that's good, what are the extended rational numbers good for? Okay, they're a way of getting the rational numbers if we wanted to, but we don't need to develop the rational numbers this way. So what else is the extended rational number system good for in practice? Well, let's start by explaining what it's not good for. So the extended rational number system is probably not good for economics. Why not? Well, when we're talking about money, dollars, then there's a big difference between a very big positive number and a very big negative number. So here is 0. Here's a sort of expanded number system where the first unit here is 1 trillion, maybe $1 trillion, $2 trillion, $3 trillion. As we go in this direction, we get more and more happy, right? It's nice to have lots of money. When we go in this direction, in the minus direction, we're talking about debt. Minus 1 trillion, minus 2 trillion, minus 3 trillion. These days, debt is a big issue around the world, and justifiably so. We are increasingly unhappy as our debt gets increasingly overwhelming. And many viewers will be familiar with national debts, which are much bigger than these big numbers here. Okay, so the point is that when we're talking about something like money, there's a big difference between a very large number, which sort of approaching infinity in this direction, and a very large negative number in this direction. In other words, plus infinity is certainly nowhere near being equivalent or the same as minus infinity. So having a number system where there's only one infinite value, where if you go in this direction and you go in this direction, you end up with the same infinity, that does not model economic situation very well. But the extended rational numbers are good for some other things. We'll see that they're good for geometry, in particular projective geometry, and parts of analysis and algebra. So maybe I should say that what number system or algebraic structure to use in a particular situation depends on the situation. It doesn't really make sense to say absolutely, well, what is finally the only way of dealing with infinity? There's possibly different approaches or different frameworks that include some notion of infinity. And some frameworks might be useful for certain problems, and other frameworks might be useful for other problems. So a few videos back I asked you to think about extending arithmetic to integers. And if you did that problem, you will have found that there was sort of a framework for doing sort of partial arithmetic with integers, where there was a plus infinity and a minus infinity, and they were different. Right? So there's not just one approach to introducing infinity as an element of our arithmetic. This is an important point. A number system is something that we create, and we give names to those things. The main criterion is that it's logically consistent and it works logically, and two, that it has some practical use. In other words, we should not be dogmatic about number systems. There's lots of them around, and we ought to be prepared to be flexible towards them. All right, so let's have a look at how we might employ infinity in the extended rational number system to help us graph rational polynumbers. In other words, to aid us in our understanding of calculus and analysis. This is just an introduction to this idea. I will probably at some later point expand on this idea. Okay. So suppose we have a rational polynumber like 1 plus 2 alpha over 1 minus alpha, which corresponds to the function in first year, usually written y equals 1 plus 2x over 1 minus x. All right, so first year students are hopefully able to graph such a function. And for us, that means, well, plotting a certain number of points within a certain range in the xy plane, and then basically joining those points to get some kind of picture of the values of this polynumber, at least in a certain range. All right, so this particular one has the property that as the value that you're substituting approaches 1, this denominator gets close to 0, so the whole thing becomes rather sensitive, and it either blows up, like gets increasingly large if the value is just a little bit less than 1, or it gets big negative if the value is a little bit bigger than 1. So this arm kind of goes up in that direction towards infinity in some sense, while this arm goes down in that direction towards infinity. There's also something like that happening on the horizontal level when the value that we introduce for alpha gets very big. Then this thing is very close to minus 2. It approaches this value here. And that's also true when the value we substitute is a big negative number. Also get something close to minus 2. means geometrically this arm is also ultimately going to approach this horizontal line, and this arm here is also going to approach this horizontal line, this one from the top, this one from the bottom. Alright, so what do the extended rational numbers do for us? Well, first of all, they allow us to substitute a certain value. For example, we can calculate r of 1. If we plug 1 into here, we will get 3 over 0. Now usually that's frowned upon, but if we have an approach where extended rational numbers are allowed, we might say, well, that's not so unreasonable. That's the thing that we're usually calling infinity. And suppose we carry on and say, well, what happens if we substitute infinity into the expression? Can we do that? In other words, if we take alpha and replace it with 1 over 0 and just do arithmetic within the extended rational numbers, what do we get? So we get 1 plus 2 times 1 over 0. Well, when you do that, that's still 1 over 0. And 1 minus 1 over 0 is also, you can check, 1 over 0. And when you do that quotient, you get 0 over 0, which is our strange number that doesn't have a name yet. However, pictorially, we saw that when the values get large, either large positive or large negative, the limit, in some sense, we haven't defined this properly, but I'm just making a suggestive symbol here, the limit seems to be approaching minus 2. This is not necessarily inconsistent, because we have this intuition that this star is kind of an open-ended thing. It sort of represents all possibilities. So maybe there's some kind of consistency here. But clearly we have to be a little bit careful about what's going on. Okay, so that's interesting, but something more interesting happens when we think about the possibility of actually pictorially visualizing this point at infinity. So down in this diagram here, I've shown you another version of this picture. It's a little bit small. It's now on a square where the x-axis here goes starting from 0 here, 1 here, and then all the way up to here, and at this point it's reached infinity. In this direction, minus 1 there, and infinity there. Similarly in the y direction, 0, 1, 2, infinity, 0, minus 1, minus 2, infinity. So there's only one infinity, so this infinity and this infinity are the same. So we really should think about wrapping this square around so that this side is glued to this side. And similarly, this side should be glued to this side so that that infinity and that infinity are really the same. What's good about that is that then this picture would be condensed in such a way that the whole thing would fit on this square. If we could somehow make this kind of compression where we replace this infinite line, which right now presently goes forever in that direction, to a very finite line segment, it means we have the potential of representing the whole graph, not just part of it, but the whole graph in one picture. And when we do that, the picture looks something like this. So we get a curve that actually goes through this point here, infinity minus 2, and then it goes up through here, something like this, and eventually it gets exactly to this point here, and then this point is exactly the same as this one. So it just carries on, and it gets to this point, and this point is exactly the same as that one. We see that in this way, the curve is actually a continuous curve in a very real sense. The remarkable discontinuity between this and this is actually somehow circumvented here by the fact that infinity is playing the role of a very big number and a very big negative number at the same time. That's what the extended rational numbers do for us. Alright, so this is not a rigorous explanation at all. This is just a bit of a hand-waving possibility for future thought. Some of you might like to play around with this to see, well, how might we compress the line and replace it with just a finite segment like that. In other words, what kind of scale would we have to use here? It would have to be nonlinear naturally. but what would be a good scale? What would be the actual shape of this curve? And if we actually did the gluing and glued the square around to form a torus, and then the x and y axes would end up being circles on this torus, then you could ask, well, what does the curve look like? It would actually be a curve going around the torus in a certain way. Actually a nice closed curve. And that kind of story wouldn't just happen with this relatively simple rational polynumber, but even more complicated rational polynumbers. We could hope that something like this could be happening, and we might be in a position to view the whole graph all at once. So that's definitely the possibility. That's quite interesting, and that's open to us by thinking about the extended rational number system. Another important use of the extended rationals is to projective geometry, where in fact, I think it's fair to say, the idea really has its origins. In essentially the work of Mobius and Plücker at the beginning of the 19th century, when they developed the idea that the projective line could be viewed via homogeneous coordinates. So let's say a few words about that story. So here's an affine line, which is just like a familiar one-dimensional line with regularly spaced points, 0, 1, 2, minus 1, minus 2, rational numbers possibly inside. There's also something called a projective line, and that's something of an extension of the affine line, where we take the affine line and we add one more point. And this point that we add is called infinity. And we think about this point as being somehow what you get to when you go infinitely in that direction. And it's also what you get to when you go infinitely in this direction. So you go infinitely in either of these directions, whatever that means, and you get to this point infinity. So which closes up the affine line to form essentially some kind of loop object. Now admittedly that's a little bit vague, but in the 19th century Mobius and Plücker realized how to make this completely precise and how to replace this kind of vague diagram with something completely cut and dried, which is very much in the spirit of the last few videos, and you'll recognize various pictures that we've shown many times. So the point is to move to a two-dimensional situation, a two-dimensional affine plane, coordinates x and y as usual, and to think about lines through the origin. So the great insight is that the projective line can be thought about being lines in the affine plane through the origin. In other words, the projective line is exactly the space of lines through the origin. How does that link with this picture? Well, you take a line through the origin, let's say this one here, and you see where it meets this particular line, which I sometimes call the viewing line. Okay? It's the line where y equals 1. So you can see this line here meets the line y equals 1 at this point here, which is the point 2, 1. So this line is labeled by that point, or by that vector in the plane 2, 1. But this line, of course, also passes through other integral points, like 4, 2, minus 6, minus 3, and others. And the idea of homogeneous coordinates is to say that we're going to agree that all of these are equal. The two little dots means a proportion. So the proportion 2 to 1 is the same as the proportion 4 to 2 is the same as the proportion minus 6 to minus 3. If we change the line a little bit, say to this one here, then it goes to the point minus 1 comma 1. And the line itself gets the label homogeneous coordinates minus 1 to 1, which is the same thing as minus 2 to 2, same as 17 to minus 17, and many others. Another important example is the vertical line, which goes through the point 0, 1, And so it gets homogeneous coordinate 0 to 1, that proportion. And another important example is the horizontal line, which goes through the point 1, 0, and so gets homogeneous coordinates 1 to 0, the proportion 1 to 0. Now this proportion is just as valid a proportion as this one, just as valid as a proportion as all the others. Of course, as a fraction, if we think about fractions, 2 over 1 equals 4 over 2. That's all right. Minus 1 over 1, same as 17 over minus 17. 0 over 1 is also a valid fraction. But 1 over 0 is not a valid fraction. But this is not a fraction, says Mobius and Plücker. It is just a pair of coordinates forming proportion. So that's, of course, exactly the same kind of thing that we're doing when we introduce our extended rational numbers. Right? We first defined our arithmetic on integral points, and then we group those points together lying on the various lines. And there was only one kind of sort of special or really odd point, which was the most important point in the picture. The point where all the lines pass through, the origin, coordinates 0, 0. And we saw that we had to sort of separate that out as a separate entity, not belonging to any of the lines officially. That's a separate object that we get to the extended rational numbers. So another way of saying it is that the projective line can be thought of as the extended rational numbers once you remove the 0 over 0. So there's a natural connection between projective geometry and the extended rational number system, where this line is just as valid a line as any other, and ultimately corresponds to what we're calling infinity. 1 over 0. Finally, I'd like to show you how the extended rational numbers help us coordinatize the circle, or in fact a general conic. So what we're going to do is we're going to augment the picture on the last slide by introducing also a circle. But it's not going to be a circle centered at the origin. It's going to be a circle which passes through the origin. And I'm going to choose the circle of radius 1, or quadrans 1, which is sitting above the x-axis with center at the point 0, 1. In fact, the story is the same no matter what conic we chose, as long as it goes through the origin. The point is that when we've done that, then the projective line of lines through the origin corresponds exactly to points on this circle. So to every line through the origin, there's a unique point on the circle. And to every point on the circle, there's a unique line through the origin. And this is without any exception. That's including the horizontal line. So for example, this line here, what's the corresponding point on the circle? Well, you just look to see where this line meets the circle. It always meets the circle at 0, 0 because the circle goes through there. But this line will also meet the circle in a second point, namely that one there. And since this is the line that corresponds to the extended rational number 2 over 1, we can say that this point has coordinates on the circle 2 over 1. This point will have coordinate 1 over 1. 3 over 1 will be down here. A half would be somewhere over here. A tenth would be somewhere over here. This point would be 0 over 1. This would be minus 1. Minus 2, minus 3, minus 20, minus 1,000. And what about this point itself? Well, that point corresponds to the horizontal line, which meets the circle in essentially a double point here. So the actual origin, which lies on the circle, is associated to the extended rational number 1 over 0, what we're calling infinity. So we get a correspondence between points on the circle and extended rational numbers without our 0 over 0. Okay. 0 over 0 does not get matched up with any point on the circle. This is then a correspondence between the projective line and a circle, which is very important in projective geometry. It's crucially important and explains many, many, many things. So there's much more to be said about this, but at least you have one very clear and good application to conics of thinking about the extended rational number system, including infinity. So now all the line is sort of wrapped around the circle, and infinity gets the pride of place by being mapped to this point here. And you can see how this naturally connects with that earlier discussion of graphs of polynumbers, because if we want to make a sort of finite picture of the line, well, this is a good way of doing it. Here's a finite picture of the whole line. We've got the whole line mapped to this finite circle with the point at infinity mapped to the bottom. That's very nice. All right, there's a lovely exercise that I want to tell you about here that's associated to this picture, which is to describe these operations of addition and multiplication on our extended rational numbers geometrically in terms of points on the circle. So for example, if we have the point 2 over 1 corresponding to the number 2, and maybe the point 3 over 1, then adding 2 over 1 and 3 over 1 gives 5 over 1. So we get the sum of this point and this point would be a point 5 over 1 a little bit further down. While the product of those 2 points would be the point 6 over 1, even a little bit further down. The question is, how would you describe or construct the sum or the product of 2 points on the circle purely geometrically, say with a ruler and compass? It's a great exercise. It's quite hard, so it might take you several weeks, months maybe even of thinking about. Okay, it's a great project, how to describe arithmetic geometrically on the circle. So we've had a few examples today of how the extended rational numbers actually can be of some use in analysis and in geometry, and there are other applications of them as well. So next time we want to get back to our main thrust, which of course is somewhat negative, to try to explain the deficiencies with a modern approach to real numbers. In particular, we want to address the idea of a limit, and can we introduce real numbers as limits of Cauchy sequences of rational numbers? Most analysts will say, well, yes, of course, that's what we do. But it's in fact wrong. It doesn't work. And I want to start to set up the necessary concepts so that we can understand the usual approach and why it in fact doesn't work, why it goes off the rails. So in particular, next time we're going to start talking about limits. We've talked about limits informally in a couple of places so far in this series. Next time we want to start being more concrete and careful. What exactly is a limit of a sequence? Now we do have sequences because we got rational polynumbers to generate sequences. We can talk about limits. We can examine the situation and start to get a sense of what goes wrong with limits. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.